Energy level diagrams. So recall that the four quantum numbers describe the location of an electron around an atom. There's the principal quantum number, which gives you the energy level, the secondary quantum number, which gives you the shape of the area where the electron is most likely to be found. The magnetic quantum number gives you the orientation of that shape. And for every orientation that there's also going to be one of two types of spin, either a positive 1/2 or a negative 1/2, denoting this last bit of information about those electrons. Now, we're going to deal primarily with the first two quantum numbers. So what we're going to do is that we are going to we're going to use the first quantum number. We're going to stick to the numbers that we have been using before. So we're going to say things like n equals 1, or n equals 2, or n equals 3. But for the secondary quantum number, the L value, the shape, we're going to translate the L value into a letter when we describe it. So if the L value is 0, instead of saying 0, we're going to switch that over to an S. If the L value is 1, instead of saying 1, we're going to say P. 2 will be changed to D. And then if we ever do use it, 3 will be called F. And this is only for the L values. So the N values will still be 1, 2, 3, 4, 5, and so on. The L values will be written as letters instead of the corresponding number to them. So when doing the calculations as to what the possible orientations could be, we still want to be able to think of the L values as numbers, but when we're talking about them, we're going to stick to numbers. We're going to stick to letters so that we can describe them a little bit easier. And it seems a bit tricky at first, but it will become easier once you do it a couple of times. Beyond F, if we did have to go beyond F, they go alphabetical after that. And the letters do stand for these aspects of them. So, as we said, the N value, the principal quantum number, is the energy level, and then the L value is the shape of the probability density. So if you're making a three-dimensional graph, you'd end up with a particular shape. So the probability of finding an electron within that particular shape is what we're talking about when we talk about the location of the electron within a particular shape. So our L value, when it is equal to 0, we're going to refer to that as S, as we said earlier. So when L values are equal to 0, we're going to refer to that S. So that shape is a spherical shape. So you can imagine a three-dimensional spherical shape. That's what we mean when we say an electron's on energy level 1, and it is in a probability of being found in the shape that is a sphere. The shape L value 1 we're going to use a P for. It has these particular shapes here. So it's kind of like a double lobe shape. And you can imagine that you can have a double lobe on the y-axis or the z-axis or the x-axis. These are the three orientations that particular shape can have. So it should start to make sense that shape S, L value equals 0, can only have one orientation. There's only one way to orient a sphere. It's the same no matter which way you turn it. But if you had a different shape, like this sort of barbell double lobe shape here, you could turn it on one of the three axes. So the reason why shape L value 1, which we're going to call P now, the reason why it has three orientations is because there's three particular ways that you can have that shape. And as we saw earlier, when L value equals 2, those are now going to be referred to as D's, there's 5 possible values. And remember, these were whatever the L value was as a negative up to the L value as a positive. So the options were dictated by what the shapes are. Shape S can have one orientation. Shape P can have 3 orientations. Shape D can have 5 orientations based on the calculations that we saw earlier. L value equals 1, we saw only had one orientation. When L is 2, the orientations were negative. When L is 1, we saw the orientations were -1, 0, and +1. When L was 2, we saw the orientations were -2, -1, 0, +1, and +2. So that options in terms of the possible orientations, we can see when we actually look at the three-dimensional shapes of these orbitals. So to describe the orbitals, we can use a number for the first quantum number, as said. So for the n values, we're going to stick to numbers, and we're going to go to these letters for the secondary quantum number, the L value, S, P, D, and when we talk about F, that's pretty much as far as we will go. That covers the entire periodic table. Remember, no two electrons can have the same four quantum numbers. So if the quantum number is describing something about where the electron is located, you're not going to find two electrons in the exact same spot. So energy level diagrams are a particular way of showing where these electrons are. It's essentially the sort of new way of drawing what we used to draw Bohr-Rutherford, and you put 2 in the first shell and 8 in the next shell. It's kind of like that, but now we know more information about where these electrons are. So instead of having a first shell, we're going to have a first energy level. Then we're going to have a second energy level and a third energy level, and so on and so on. But the options for these energy levels are going to be a little bit different. The first one, so the first option where you can put an electron is going to be on the first energy level. So we're going to write, so this would be, imagine this being n equals 1. And then that would be the first energy level. We know that when n equals 1, the shape is 0, which we're now going to call S. So we're going to use a circle or a square or just some sort of space that represents that particular shape. And we don't have to draw the shape accurately. We just need a space to put electrons. So we're going to say, okay, this is going to be shape 0, which we're now going to call S. So this spot right here is the first energy level, and we know that it has shape S to it. So we just call it 1S. We know that if it has a shape S, there's only one possible orientation. So we're only going to go one spot. And for each orientation, there's 2 possible spins an electron can have. So we're going to put 2 possible electrons in here. Instead of writing -1/2 and +1/2, we're just going to draw an up arrow to represent one of them, let's say +1/2, and a down arrow to represent -1/2. It doesn't matter which one's which. We just need to know that there are one of 2 possible aspects of the electron in that particular orientation, in that particular shape, on this particular energy level. Now, when n equals 2, the second energy level, we knew that there were 2 shapes. There was the 0 shape and the 1 shape, which we're now going to call the S shape and the P shape. The S shape has 1 orientation, so we're going to just have 1 spot to put electrons, but the P shape, when we have an L equal 1, we have 3 possible orientations to that. So we're going to need 3 spots where we can put those electrons. And then within each of these orientations, we're able to put 2 electrons, one with 1 spin on it and one with the other spin on it. It doesn't matter which one you do first. I'm just using arrows to denote one of 2 options. And then when we have n equals 3, same thing. We had shape S, we had shape P, and then we also had our shape D. L equals 0, L equals 1, and L equals 2. And when L equals 2, we could have 3, think of this as our -2 orientation, -1 orientation, our 0 orientation, our +1 orientation, and our +2 orientation. So we have 5 possible spots to put electrons, and there can be 2 electrons in each one of those spots. So energy level 3 has shape S, shape P with 3 orientations, and shape D. So I can label this as 3D. It has 5 possible orientations. Each one of these orientations can hold 2 electrons. So the shells themselves correspond to the energy levels. The circles that I've drawn on here represent the orbitals. They can be drawn as rectangles or just spaces where you can put electrons. And the different shapes that you have within a particular shell we call subshells. So the rules for putting electrons into these spaces. So here we have level 1, level 2, level 3, and I haven't finished off with level 3D, and we'll talk about that a little bit later. But there's a few rules that we need to follow when we're putting electrons into these spaces, these areas around the nucleus. So we must follow these rules. The first one is an Oafbow Principle, and it says that the lowest subshell must be filled first. So electrons want to go to their ground state, so they will always go down to the lowest energy level that is available. So we're going to start putting electrons there first. So if we use an arrow to represent one of the spins, we can put one electron in the lowest energy level, which would be principal quantum number 1 in shape S, and we can put one electron there. If we have two electrons, we can put it in that same orientation, same shape, same energy level, but it has to have a different spin. If we had 3 electrons, that first orbital is full. So we would have to move up to the next one, and we'd always go to the next lowest one. So if we had 3 electrons, we'd have 2 in the 1s orbital, and we'd have 1 in the 2s orbital. And then if we had 4, we could put that fourth one in with the third one in the 2s orbital. A fifth one would show up in one of the 2p orbitals. And again, we're using arrows to represent the electrons. Let's say the up arrow represents a positive half spin. The down arrow represents the negative 1/2 spin. It doesn't matter which one's which. We just need to put one of each type in each orbital. Second rule is called the Pauli Exclusion Principle, and it says electrons can't have the same 4 quantum numbers. So this is the point of drawing the up arrow and the down arrow. We couldn't put 2 up arrows in the same orbital because that would suggest that they have the same spin. So we put one with one spin and one with the other spin. Hund's rule says that the orbitals within the same subshell, so if they're a p subshell, or like we have here, or a d subshell, if I kept drawing them here, must each get 1 electron before pairing can occur. So let's look at how this would look. So if we put 1 electron, it would show up in a 1s orbital. 2, they both fit in that 1s orbital. 3 electrons, we need to put 2 in the 1s orbital and 1 in the 2s orbital. So say that would be a good representation of where lithium would be putting its electrons. So put 2 in the 1s orbital, and then that orbital is full. You'd have to put the third one in the 2s orbital. You can put a fourth one in the 2s orbital. When you get a fifth one, you're going to have to put in the 2p orbital. Now here's where Hund's rule comes into play. When I go to put a 6th electron in there, I'm not going to put it in this same orbital here. What I'm going to do is I'm going to spread them out across this subshell here before any of them get paired. So the 6th electron is going to have to show up in this orbital, not be put here as a down arrow. It's going to be put there as an up arrow. We spread them across the subshell first before someone gets a pair. So this one here, we have 7 electrons in there, and we have an even distribution of electrons across the subshell. Before, if we went to an element that had 8 electrons, then we would start to pair them. All right, and so the corresponding relationship to the periodic table can be seen in the way that these are arranged. So if you look at this, we can see that 2 electrons get put in the S subshell. In the P subshell, 6 electrons get placed. And the first energy level has 1 subshell. The second energy level has 2 subshells, an S and a P. And the third energy level has an S, a P, and I haven't drawn it here, but it also has a 3D subshell as well. The number of electrons that you can fit within each subshell depends on which one you're talking about. If you're talking about a 2s, you can only put 2 electrons. If you're talking about a 2p, you can put 2 in this one, 2 in this one, and 2 in that one, for a total of 6. So the different subshells can hold a different number of electrons. And this is how we built the periodic table. You can imagine helium over here really should be right there. In terms of the quantum mechanical model, that's the best place to put it. The first period represents the first shell, the first energy level. And in that first shell, you can fit 2 electrons. So these two would be the place where you'd put the 1s electrons. Then the 2s electrons, if we go back up here, these guys, let's go back to where we just have 2s. These two here get put in the 2s 2s orbital. That corresponds to the second row in the periodic table. You can have one electron here and one electron there. So imagine lithium. So lithium would have one electron in its 1s subshell. It could fit a second electron in that 1s subshell. So if these two here represent the 1s 1s orbital, you can fit 2 electrons in that. Then it's full. So if your third electron is going to have to show up in a 2s orbital. So think of these two boxes here represent the 2s orbital. You can fit one electron before it is with each of the spins before it is full. But once you have 2 electrons there, it is now full. And if you go to put down 5 electrons into an atom, you can fit 2 in the 1s, 2 in the 2s, but then the fifth one has to show up in a p orbital. And the second energy level has a p subshell. There are 3 different orbitals. So you can imagine if this spot here on the periodic table, that represents our 1s subshell. It can hold 2 electrons. Our 2s is the next one to get filled. It can also hold 2 electrons. So you can imagine we can put a spin of 1/2 positive, there's an arrow, and a spin of 1/2 negative, and then it is full. And then you have to start filling up your p subshell. So we know that a p subshell has 3, they're kind of funny looking circles here, 3 orbitals to it. So you can relate the quantum tree to the periodic table. Each one of these can hold 2 electrons. So I'm going to follow the proper Hund's rule in that we should put 1 in each one before we pair them. But you can imagine if we were to go and draw neon here, we would have one, draw those electrons in a 1s. 1, there's another arrow there. So the 1s would have 2 electrons in it. The 2s would have 2 electrons in it. And then the 2p would have 1, 2, 3, 4, 5, 6 electrons in it. That is what the energy level diagram, it's kind of upside down here, but that's what an energy level diagram for neon would look like. It's filled them up here. So essentially, the blocks on the periodic table correspond to the subshells that we see within our quantum tree. We have an S block over here, we have a P block over here, and we have a D block over here. And the number of elements that fit within the block corresponds to the number of electrons that you can fit within those orbitals of that block. So for example, the S block is only 2 elements wide because an S orbital, that subshell, that orientation can only hold 2 electrons. A P is 6 wide because there's 3 orientations. Each one can hold 2 electrons. A D, and remember this is representing our L value. Our shape here is 0, and we have a shape of 1, and we have a shape of 2. So let's just do that. So the possible L values, let's do our L values. For the S, we're talking about an L value of 0. For the P, we're talking about an L value of 1. So if we had an ML value, that's ML, if the shape is 1, we know there are 3 possible orientations for an L value of 1. We could have -1, 0, and 1. That's 3 orientations, and each orientation can hold 2 different electrons, each with a spin that is different. So that's 6 spots. So that is the P block there. When L equals 1, we're talking a P subshell, and there's 3 orientations, 2 spots each. That's 6 wide in terms of how many electrons you can fit there. So when L equals 2, we use the letter D to represent that one. So we call these guys here, the transition metals, the D block. we know that if L equals 2, then ML has 5 possible orientations, and each orientation can hold 2, so 5 times 2 is 10. So the transition elements block is 10 wide. See if you can figure out how wide the F block is. All right, so notice how the electron configurations correspond to the arrangement blocks on the periodic table. For the subshell S, we have 2 electrons that can fit there, and the S block is 2 elements wide. P can fit 6 electrons, the P block is 6 wide, D is 10 wide, and F is 14 wide, corresponding to the number of spots to put electrons based on the orientations for that particular shape. Some complications of this are that when the electrons are being placed, so we can think of drawing our quantum trees, the branches that we're forming, so if these are the principal quantum numbers 1, 2, 3, 4, and we look at the possible subshells that they have, subshell 2 has energy level 2 has a subshell S and P, 3 has S, P, and D, 4 has S, P, D, and F, which is fine. The problem is, as we get higher, some of these subshells start to overlap. So, for example, yes, 3 does have a D subshell, but the 4S subshell, the first subshell of the level 4 energy, buds in front of the 3D, the last energy level. So the first one of the 4th energy level comes before the last one of the 3rd energy level. That's a complication. So knowing that happens is fine. Knowing when to do it is going to be a little bit more tricky. So if we look at this one here, the bottom's being blocked, but the 2 P's get filled, and then according to the rules, we have to fill the next lowest one. So after 2P, the next lowest one is 3S. After 3S gets its 2 electrons, then we go ahead and fill in the electrons on 3P. And you'd think that 3D would come after 3P, right? Because it's all the same energy level. But it turns out that 4S is actually on a lower energy level than 3D. Trying to predict that would be very difficult. Thankfully, the solution is in the periodic table. So if we know that this is the S block, and we know that this is the P block, and this is the D block, we just follow along with what the periodic tells us. It tells us the order. If you know your number line, you know the order. 1 comes before 2, 2, and then 3, and then 4, and then 5, and 6, and so on. So that's pretty easy to follow. So as we're replacing electrons, we put them in the 1s first. And again, helium really belongs over here in terms of the quantum model. So that the 1s orbital is filled first, and then the 2s orbital. And after your 2s orbital, where do we go? Well, what comes after 4? 5. And this is a p orbital. We know it's a 2p. It's the first of the p's. There is no 1p because, again, based on the rules for the quantum tree, there is no such thing as a 1p. Energy level 1 does not have a p subshell. So after 2s comes 2p. That gets us to neon. And then when we go to place an 11th electron after neon, number 10 comes number 11. So that's back to our S subshell. So we know 3S comes next, which is what we'd expect. Once 3S is filled with 12 electrons, and let's say we wanted to place a 13th, we'd have to jump all the way over here to aluminum, and then we'd be starting to fill another P subshell. Here's where it gets tricky. That's a 3P, so we did 3S, and then we did 3P. You'd assume that 3D would come next, because there's a 3D. But as the periodic states, there's argon with number 18. It has 18 electrons. The 19th electron, so potassium's valence electron, is going to be placed in a 4s subshell. 4s gets filled before 3d. You don't need to guess whether that happens because the periodic table tells you that that happens, because after 18 comes 19. And 19 is a member of the S block. It is 1, 2, 3, 4. It's the 4th row in the S block. So we know that that 4s is going to be filled. And then once you get to number 20, then comes 21. So this is where we start filling in our 3d orbitals. And we know that there are 1, 2, 3, 4, 5 orbitals there for our d level electrons. 2 spins per each one gives us our 10 electrons. And then just keep following the numbers. So, energy level diagrams for ions. We can look at some of the multivalences that ions have, and we are able to explain them using these energy level diagrams to see where the electrons are coming from. If we look at an anion, they're really easy to do because we've been working on placing electrons. Anions just have more electrons, so you just keep following the same rules and you put in more electrons into the energy level diagram. Cations are a little bit harder. So cations are positively charged. They've lost electrons. So when you have an energy level diagram with some electrons in it and you have to make a cation, you've got to take some electrons away from there. And generally speaking, you'd want to take the electrons away from the highest n orbitals first. So not necessarily the last ones that you put in, but whichever ones are from the highest n values. So let's say we had iron here. If we wanted to draw an energy level diagram for iron, we look up how many electrons it has, and this is where they'd all get placed. So we'd put 2 in the 1s, 2 in the 2s, 1, 2, 3, 4, 5, 6 in the 2p, and you keep going all the way across. You'd put every 1 in each of the 3ds before you paired that last electron up in the 3d level here in this particular orbital. But if we wanted to do iron 3+, so it's as a cation, we've got to take iron's electron configuration and we've got to get rid of 3 of these electrons. The thing is, we wouldn't just take out the last 3. So you can imagine that the last electron that we put here, this guy right here, and then the second last one, this guy, and the third last one, that guy, we don't just take them out. What happens when iron is a cation is that they're removed in a way that tries to leave the atom as stable as possible. So the trick is to figure out what is stable in terms of atoms. And one of the things that we see is stable in these ions is that they like to have half-filled D subshells. So there's lots of things that can make them stable. A full P subshell is really stable, and we know that because all the noble gases have a full P subshell. But another thing that makes them stable, especially when you're dealing with transition elements, is having half full D. So if you have 1 electron in each one, that would be half full, spread evenly across the board. That turns out to be a stable configuration. So when you're making a cation and you've got to get rid of electrons, so here we've got to get rid of 3, try to do it in a way that leaves them half full D subshells when possible. That tends to be a fairly stable configuration. So if we were to see 3 electrons removed from here, if we took the 2 out of the 4s and this 1 out of the 3d, that would give us our charge, so that's no problem. And it leaves us with a half full 3d subshell. So that ends up being a relatively stable configuration. So that is one explanation as to how iron could have a 3+ charge. So generally speaking, what makes atoms stable, it kind of depends on which atom you're talking about, but there does tend to be some particular trends. It is a little bit complicated. Just because you put them in a certain way doesn't mean you're going to be taking them out that same way when you form a cation with that atom. But general rules for stability would be a filled subshell is great. It's like a filled 2p. Noble gases have them. They're really stable. Everyone loves that. But if you can't have a filled subshell, generally a half-filled subshell is the next best thing to do. And then after that, you just have to deal with what you can in terms of stability.